Swayam Prabha. Digital India. Educated India.
Good morning everybody and welcome to our course on Introduction to Micro Machining Processes. In the last class we have seen some of the aspect of micro machining, and that was related to the how the size effect affects the different type of mechanism during material removal. And we have seen that how the cutting edge angle of cutting tool that affect the different types of phenomena, that we have seen that one of them is the shearing, that is what is required in the machining. Second one was the extrusion, in that some of the material is moved as a chip and some of remaining part will be become a part of the machine surface. Third one was the rubbing of the surface, and fourth one was the ploughing. And we have also seen that ploughing and the rubbing should be avoided, so that you can get the required geometry or the required machine surface without any problem. And then we have seen some of the phenomena of the ductile machining, that when defects are present in the raw material, then there is a chance that the material, yes. Okay. And we have seen in the last lecture also that we need some defects, so that material can be removed very easily, where the propagation of the crack will pass through these different type of materials, and that is very easy to explain in these particular slides. Yes. And we have seen that what are the different defects available, that is mostly the pore, impurities and some type of other foreign elements also. And these are the different stages through which the material get fractured, starting from the inclusion, and then it will pass through these different steps. And then we have seen that what is the effect of the presence of this defect during the material removal, and we have found that if the defect levels are very high, you can easily remove the material, but we know that we are removing material at micro scale. So, that is the reason that our uncut chip thickness will be very small. This is the right now what is available, but our uncut chip thickness will be very small in this case, and that is the reason the number of the defects will be very less, and that creates a problem in the machining. So, you need a very high amount of forces, and we have seen the material resists plastic deformation much more strongly than expected due to less defects. And what is happening because of that? We are working with a small HC, that is the small amount, very small value of the uncut chip thickness, that is HC here. And what happens because of this? The deformation will happen at a small scale, that is what is showing here. And when deformation is small scale, we know that the tool will encounter less amount of defects, and that is the problem with the material removal, and because of that you are end up with the high material strength of this, because material will behave like a more ideal ideal material without any defects, and that is the reason you are getting a very high strength of the material at the micro scale machining. Now, what is the effect of blunt tool? Because till now we have seen some of the examples that where we are talking about the cutting edge radius of the cutting tool, where we have seen that it is not ideally sharp cutting tool, and we always have some radius that is called cutting edge radius. So, what will happen because of the blunt tool causes some pushing of the material, that this diagram we have seen that pushing of the material happens in different directions. So, there are different locations. Let us identify those locations first. So, let us put this one is the one. So, that is called immediately ahead of the cutting edge into the chip. So, now this is our the chip flow. So, when this is the material, now if you see from the side view, then our tool is here. Let us right now consider as a sharp tool, and this is our chip, this is our material, this is our uncut chip thickness, and this is our machine surface. Now, when it is removing the material, this is the tool, this is the workpiece. So, this is immediately ahead of the cutting edge into the chip. So, whatever this portion is there, this portion will be here. So, and when it continues at that time, some of this part will come out as a chip, while some of them will be moving here and there, that we will see here in the next 2-3 topics, right. So, what happens because of that? First, that some of the material will go ahead into the chip. Second is the into the machine surface. Now, this is also the machine surface location. Now, in the last class we have also seen this particular thing, that some of the materials will move ahead into this particular location, that is because of the location of this particular point D and because of this blunt tool. So, whatever is HC is there, some of the portion of this HC will go as a chip and some of them will again become a part of the machine surface. So, these are the two things, and possibly to the sides also, that we have seen in this particular diagram. So, now you can see that this whatever material is in this particular location, whatever we are looking at this part. So, this is at the front zone, and we know that our tool is moving in this direction. So, ultimately when tool approaches in this direction, whatever material is present ahead of the tool, that will be considered as a chip also, because at the end this whole material will be scooped out by the tool, but part of this material again become the machine surface, some of them will go to the side and some of them go to this sides also. So, this material will not play a major role, but what is happening to this particular material, that will be very interesting to understand by these two examples. That some of the material become part of the workpiece surface. So, machine surface some of the material will go. So, ultimately you are not effectively removing the material and possibly from to the side. So, this side is the again the plowing material. So, you are just plowing the material from this side. So, your surface will be something like this. This is the cut zone and these are the material which is piled up on the both the sides because of this plowing effect, correct. Now, let us see the what are the different type of examples with respect to the material and the machining parameters. So, first one is the grain size to the chip thickness. So, material cannot be treated as isotropic and homogeneous like in the conventional micro machining. So, now this is the example. Now, what this figure tells us, that this one is R and this one is D. So, this one is considered HC, what we are just nomenclating it HC, and this one is the R, that is the cutting edge radius, and this is our conventional machining. And we can see here that these are the small grains. These are not actually small, but because of the scale of this macro machining or the conventional machining, it looks like a very small in this case. And we consider our cutting edge radius is sharp and our R is much better than or much larger than the uncut chip thickness, and this whole material come out as a chip, and our alpha, that is the rake angle, is also positive. So, no problem in this case. And we can also clearly see here that there are many layers of grains here that will come out as a chip. So, machining through this grain boundary is very easy to perform in this particular case. And size effect also affect the plastic behavior by creating the geometrical constraint, obstruct dislocation to initiate and slide. Now, consider this example. This is the same thing, but at a micro cutting, at micro level. Now, many things are changed here. First thing is the R is not smaller than the D. So, you consider R equal to D or R is bigger than D. So, in that case, our sharpness of the tool also play important role here. So, now we have to put R here. Then what is this R? So, this R may be equal to HC or it is bigger than HC in this case. So, now our effective rake angle is negative in this case and our material removal will be different. Now, if you see the grain size here, you have seen here that there are many grains which are coming out as a chip, but that is not happening here. Now, you can see that if you draw one line through this particular line, then you can see that this whole grain is going to cut when this tool will approach to this particular grain, and other than that some of the grains are individually oriented and located randomly at different location, and because of that you have to create a lot of amount of energy here to remove that material or to fracture this particular grain. So, what size effect tells us? The size effect also affect the plastic behavior by creating geometrical constraints. So, those are the obstruct, dislocation to initiate and slide. So, we are not able to get the one particular dislocation. Dislocation means the defects that through which the material will be removed, or that particular cutting will initiate, or the crack propagation will initiate. But that is difficult to find here, because now we are looking at individual grain, and some of the grains are exactly reaching to the center of this particular line, and that is difficult to cut through this material, and these are the very difficult to measure and find out the further possibility of cutting of this material. Now, coming to grain size to feature size. Now, in conventional machining we have seen that our tool is very large, that means comparative to the size of the grains, and we can see this particular diagram that this is our end mill cutter and this is the amount of material we are removing. So, we are cutting from the side. So, this is the vertical side and this is the bottom side, and you can see the number of grains which we are cutting from here. These are very large in terms of numbers and in terms of layers also. But if you see the same thing at a micro scale, suppose we are considering the feature size around few of hundreds of micron, then sometimes the grain size is also similar to that dimension. So, what is problem in this particular case? That when you are cutting a material, because your cutting tool has also grain structure, and when you are talking about the cutting tool diameter, consider 200 micron, then you have to use very fine particles of the tungsten carbide and cobalt, so that you are end up with the very large amount of grains, so that you can get the required geometry to cut onto the cutting tool also. So, now here because of this, what are the problems? Let us see. So, when the micro features and grain size are comparable in size, now we want to cut the material at a micro scale and which has a feature size of 100 micron or something, and we have a grain size also in terms of hundreds of micron. So, grain size and the feature size are almost same. So, material behavior is different in this case, cutting mechanics changes due to the size effect. Now, what happens in this case? Why material behavior changes? Because now if you see this particular thing and you are cutting this particular line, we have already discussed, but let us go a little bit more in depth. So, when you are cutting this material, two things happen. First thing is that your tool will be loaded severely in this particular case, because now you getting a boundary of the grains or the getting a defect to initiate or slide the dislocation, it is very difficult in this case, because 1, 2 and 3 grains are only coming into its picture when you are cutting the material. So, material behaviors are different. Now, everything depends on the size of the grain, size, distribution, orientation of the grains. Now, size also matters, that we are discussing here. Distribution, that means how they are distributed. Orientation also makes difference, because if they are uniformly oriented, then there is a chance of, that is something like this. These are very ideal structure, and suppose your cutting tool located here, then it can find a grain boundary very easily, and that grain boundary is continuous in this case. But now, if they are located something like this, that is what this is the structure, then there is a problem that you may not encounter this particular boundary to initiate the slide cutting. And because of this different phenomena, what happens, the cutting mechanics changes due to size effect. Cutting mechanics, that means now you have to look at to the individual orientation of the grains, because earlier we were ignoring this thing when we are cutting at the macro scale or conventional machining, but we have to also see the microstructure of the material which we want to cut. So, in this case you have to think very deeply to get into the machining zone, so that you can get the more information about the characteristics of the grains of the material. Now, ductile to brittle transition with depth of cut. Now, till now we have seen that we have problem with the depth of cut. Depth of cut means uncut chip thickness. Now, what is going to happen if you increase the depth of cut of some material? So, let us take one example of the PMMA. So, this is one of the polymer material and full form is the polymethyl methacrylate, and this material is well known used for the different type of microfluidics devices, because it is very transparent also, and you can get a micro machine channels very easily, that we have seen in the example application section of the our course in the first or second lectures. So, now let us see. So, these are the high speed images of the cutting tool. So, this is the cutting tool. So, this particular thing is the cutting tool. Right, this is the PMMA material and this is the chip, right, and here depth of cut is very small. Small depth of cut. Now, you can see that the whole chip is coming out as a curly part. So, it is a good sign of the cutting. So, we are getting a clear chip out of this, and this is considered as a shear mechanism or the shear mode of cutting. Now, we have increased this depth. So, let us see that now comparatively more depth of cut. Now, there are two ways to look into this thing. First thing is the chip. Now, see, chip is still curvature, but these are very segregated. If you see this particular thing, these are very segregated. And another thing is this machine surface. If you see this thing, machined surface, and see the same thing here. Now, you can see here it is very clear surface. That means, there is no material is left uncut, or no any fracture happens, or no cracks, nothing is here. But if you see this particular location, you can find a very clear layer here which is deformed. So, this is the deformed layer, due to more depth of cut. Okay. So, let us continue further. Let us increase the depth of cut little bit more. So, now we have further going down into the material, and now you can see the removal of the chip is little more difficult. In first, second and third one, you can see that now material is not removed very efficiently. Chip is not in curvy nature, but some of the things is very bulky, and some of the thing is very thin here in this case. Now, if you see this particular thing is very bulky, and here you can still get one curvature, but see the machine surface deformation, it is very prominent here in this case. So, it is not the efficient cutting. Let us further increase this thing. Now, this is even more depth of cut. So, this is higher depth of cut, and this is very high depth of cut. Now, in this case, now what is happening here in this case, that now material is getting fractured severely. Now, if you see, this is the material. Now, if you see the boundary, so this is the boundary of the material, and now you can observe here the tool is not in contact with the workpiece at all. because when the depth of cut is very high, what happens, the fracture initiates instead of a plastic deformation, and many material ahead of the tool will come out as a discontinuous chip or a segregated material because of the high depth of cut and the high velocity in this case. And that is why you will encounter some of the instances where your tool is not in contact with the workpiece surface. So, that is happening when you are machining some polymer based material or some type of glass material where the depth of cut is very important to in this type of material removal things. Now, how to observe or how to get information out of this thing, because if you consider this thing is happening at a micro scale, even though we are telling that depth of cut is very high, but if you see at micro scale, we can higher depth of cut we can consider as 100 micron or 200 micron or something, and this one is the lower case, that means in terms of tens of micron. So, we need to get this information by some other mechanism, so that we can understand that what is happening into the machining zone. So, one of the ways of doing this thing is that we can find out what is the force is acting onto the material. So, you put a dynamometer onto the workpiece, right. So, what we are doing, that let us put one dynamometer on the top of the workpiece, we are putting this, and then we are cutting with the cutting tool. So, this is the tool, this is the workpiece, this is the dynamometer, force transducer, transducer, and then when it is cutting, it will give you one signal, and we have to observe this signal to get the information about the machining zone. So, what is happening? So, let us draw one graph with respect to the travel of the tool on the x axis, and y axis it is force. Right. So, this is the diagram belongs to the first cut. Now, if you see in this case, so this is the tool travel. So, tool is moving in this direction, and we are measuring the forces, what is happening to the forces. So, initially when it is not in contact, so you obviously get a 0 force, and when you are penetrating into the depth, suppose this tool is gradually going into the material, then the forces will increase suddenly, and then when you are moving in this direction, that is in feet direction, your force will stabilize in a particular band or particular range. So, now if you see this variation is very small in this case, right. So, this variation is because your depth of cut is very small, amount of material which is removing out of this workpiece is also very small. So, your force signal is somewhere here. So, let us consider this one is a reference signal, and we consider this one as a small signal, but we are not getting any type of disengagement between the workpiece and the tool, because tool is in full contact with the workpiece throughout the cut. So, this is what is getting. So, whatever this variation is there, this variation is because of the many reasons, that machine structure also play important role here. There are vibrations occurs, stiffness of the machine tool is important, and the cutting mechanics, the material, which material you are cutting, that also creates this signature. This we will discuss in more detail in sensor part, but let us right now consider this variation is unavoidable, many times you get these things. Now, let us move to this next figure. So, when you are getting a continuous chip, your steady cutting forces are occur. So, this is considered as a steady cutting force. Now, coming to the next part. Now, what is happening here in this case, that your chip is not similar to this chip. Now, your depth of cut is increased little bit, and if you see this particular diagram, so now your variation in the cutting force is also little high. So, now it was oscillating a very small amplitude. Now, this amplitude is increased, because now you are getting some fracture onto the machine surface, and your chip removal is also not very efficient compared to this first figure. So, now your oscillation is very high, but still it is in full contact. That full contact means you are not getting any type of cutting like this, something like this. So, there is no any type of open region between in the signal. So, still it is in full contact, but your amplitude is increased, that means you have a large variation in the forces. So, this variation also plays important role in the life of the cutting tool as well as the workpiece material quality. So, let us see the third graph. Now, this one is the third one. Now, in this particular case, if you see this machine part, there are large amount of deform or the fractures or deformation or some type of unwanted things here at the machine surface. And chip is also different now, it is coming in a very awkward situation, means you are not able to identify the which particular shape of these chips are there. So, now in this continuous fashion, now your still it is in full contact now, but what is happening, that force variation is very large in this case, because sometimes it is able to remove material very quickly and then suddenly it jumps to the downwards, because the material which is just ahead of the tool is already fractured, that means the crack is already initiated before it is reaching to the surface. So, when tool is reaching to that location, tool does not require so much amount of force. So, it removing this much amount of material. So, now again the fresh material is coming. So, again you need a very large amount of force, and that particular large amount of force is again coupled with the loose material which is in this case. So, you are getting a very high fluctuation motion during this cutting at a high depth of cut. So, now let us move to the next slide, next topic, this is the thing. So, now here we have seen that there are many different things compared to these first three. First thing is that your tool is not in full contact. So, this is the surface of the workpiece which is machined, and chip is also not visible because it is a pure fracture now, it is not removing as a ductile material. So, what is happening, that when you are machining with a small depth of cut, you can cut a brittle material also in ductile mode. So, that is what is happening. So, if you increase the depth of cut gradually, what is happening, that your pure nature or the actual nature of the brittle material comes into picture, and then it will do machining at a brittle fracture. What is the brittle fracture? That means, if you hammer a glass, you will never get a chip, but glass will be scattered. So, same thing is happening in this particular case. So, once the tool is in contact, initially it is touching the surface, then let us, this is the tool travel. So, it is traveling the tool in this direction continuous. So, initially this is the depth of cut is very high. So, your force is increased, and along with that it is moving in this direction. So, it is removing this much amount of material. So, now if this is the situation, you are getting a off time, that means you are not in contact with the surface, tool is not in contact with the surface. So, this is the non-contact region. So, your tool has removed this much amount of material, it is scoop out this material, and then tool is coming into contact this. So, after off time again you will get the same peak and the same fashion of this particular first trend, and again you are getting this removal. So, now what is the important thing, that when you are cutting a brittle material, your depth of cut is very small, then you are able to remove the material in the ductile mode and you can get easily chip. And if your depth of cut is very large, there are two things happening. One is the tool will get damage, and another thing is your workpiece is also degraded. Quality of workpiece surface is down. So, this thing is more important in the precision machining, where we will cover the diamond turning operation, where our depth of cut is in a 1 micron or less than 1 micron, and you are cutting the silicone and some type of brittle material. So, here our objective is that it is not always necessary to maintain or go with the higher depth of cut, because we have seen in the earlier example that your uncut chip thickness should be higher than the cutting edge radius. So, here also it is the same thing, but here that ratio is very large in this case, because you have penetrated your tool such a large extent that your material property is playing important role on the negative side, because now your depth of cut is very large, force fluctuation is very large, your stability of the tool is also questionable. So, this whole thing will end up with the low quality of the surface as well as damage or the breakage of the tool. So, let me finish this lecture here. We will continue this topic in the next class. Thank you very much.